Okay, hello everyone. This video I'm going to show you the statically indeterminate in axial loading. Okay, and here is the second example. Okay, and in previous find the equation, another equation by yourself to solve the problem. Okay, because after you're doing the force balance or moment balance, you will find you don't have enough equation to solve problems. So you need to find a so-called competitivity equation to solve the statically indeterminate problem. Okay, and here is the second example in axial loading. Okay, and here is the member is a coaxial bar. Okay, coaxial bar. And the coaxial bar, it's okay. So it say the core is brass. Okay, core is brass, and the shell is aluminum. So this looks like this. Okay, so there is a core. It's a coaxial bar. Okay, the core is brass. Okay, and the shell. Okay, maybe it doesn't look like a circle. Okay, but okay, but just the shell. Okay, the shell is aluminum. Okay, it's a coaxial bar. Okay, and he said the problem said we apply a axial compressive load. Okay, 45 kilonewton pressed down press down to this bar, but I think this picture will generate some misleading. Actually, it should be look like this. Okay, it's called, and you apply a average load. Okay, so overall is 45 kilonewton. Okay, and this picture you will think you only apply the external load on the core. No. Okay, actually the problem means it applied the 45 kilonewton. Okay, on the coaxial bar. Okay, coaxial bar. Okay, and vary in average way, in average distribution. Okay, 45 kilonewton. Okay, and so determine the average normal stress and aluminum and brass. Okay, and so you apply the external load on coaxial bar. Okay, but we apply the same external load to the coaxial bar, but the brass and aluminum will share the normal stress. Okay, and brass has contributed normal stress. Also, aluminum also contribute to normal stress, but their contribution are not equal to each other. So, the problem I want to ask: what's the normal stress for the brass, and what's the normal stress for the aluminum? Okay. So since this bar is apply a compression loading. Okay, so okay, the same thing. Okay, so we also use the cut section method. Okay, we cut section here. Okay, we cut section here, and if we cut section here, okay, I'm sorry, this is another. Okay, so we cut a section. Okay, we cut section here. I need to use the same color. Now we cut section here. Okay, we cut section here, and there's the internal force. There's an internal normal force, or to balance the external loading. Okay, there must be an internal normal force to balance the external loading because the whole object is static. So, okay, so if you do the balance equation, we will have, okay, this m point up and 45 point down. So, m point up and 45 kilonewton point down equal to 0. So, we already know the internal normal force is 45. So, kilonewton point up. Okay, it's point up. And also, but be careful. Okay, so we say those are the overall internal normal force also 45 kilonewton, but I say the brass and aluminum share the normal force. So this normal force is contributed by two material, core part and shell part. So, okay, so we just assume, okay, we have core is brass. Okay, we have shell aluminum Al. and plus together is equal to N and equal to 45 kilonewton. Okay, so that's what we got from the rigid body equilibrium. Okay, and the problem want to determine the normal force on brass and normal force on aluminum. Okay, and after using the rigid body equilibrium, we have found this equation, but we have two unknowns, so it's not solvable. So this so-called statically indeterminate. Okay, and you found that your problem is statically indeterminate. That means you need to find more equation to solve the problem. Okay, so what's the other equation in this problem? Okay, so because this coaxial bar is subject to the average external loading. Okay, so it will lead to this competitivity condition. Okay, the strain of the brass is equal to the strain of aluminum. Okay, because it's compressed. I'm not sure you can imagine this. The external is compressed. Was compress this average bar. It's compressed. Compress this every compress the bar, coaxial bar. Compress the coaxial bars. Okay, and it's compressed together. Okay, so because and these two material must be hold to each other, so it compressed together. The core and the shell will have the same strength, especially or more specifically, the core and shell has the same normal strength. Okay, because it's coaxial and these two parts is subject to the one external loading. So they must be okay. The strain, normal strain, the core and the shell must be the same. Okay, so this is another condition, and so it's called competitivity. So this equation is so-called competitivity equation. Okay, and let's see if we use this competitive equation, what do we get? Okay, and don't forget the strain, the formula for the normal strain. The formula for normal strain is, okay, I write down here. Okay, the normal strain, the formula for normal strain is normal force times L divided by area times the elastic modulus. Okay, elastic modulus. Okay, so this equation, so okay, we continue use this equation. So the strain, normal strain of the brass, so the normal strain of the brass times the L of the brass divided by area of the brass and times the elastic modulus of the brass and equal to normal stress of aluminum times the L of aluminum and divided by A of aluminum and times the elastic modulus of aluminum. Okay, and because it's a coaxial bar, so the length of your brass and length of aluminum is the same. So okay, you can cancel this out. Okay. Okay, the normal force on brass and normal force on aluminum, we don't know. Okay, so keep it. And do we know the area of the brass and area of aluminum? Yes, we do know because this problem gives the radius, outer radius 50 millimeter and inner radius of 25 millimeter. Okay, so based on this radius, we can calculate the area of the brass. Okay, what's the area of the brass? Okay, we need the space. Okay, the area of the brass is it's give you a radius, so it's pi r square. Okay, it's pi r square is 25 times 10 to the power minus 3 square. Okay, and what's the value of this? Okay, so we need to calculate 25 times 10 to the power minus 3 square times 3.14. Okay, so it's 1.9625 times 10 to the power minus 3, and it's millimeter square. Okay, so what's the area of the aluminum? Area of aluminum is a little more difficult because it has a hollow in there, so it's a pi r square minus pi r square. Pi 50 times square minus pi 25 square. Okay, so I hope you can understand the calculation of the area. Okay, so what is this value? Okay, And let me see. Okay, so pi 45 times power minus 3 square minus 25 times 25 1000 1000. Okay. Mm-hmm. Did I calculate right? Oh, I forgot the times. 3.14. Okay. So it's 5.8875 10 to the power minus 3 meter square. Okay, so that's the area of the present area of aluminum. So we have this. And finally, this problem gives us the modulus. Yes, it gives us the modulus. Elastic modulus of aluminum is 70 gigapascal, and elastic modulus of brass is 105 gigapascal. So we also already, and okay, we put all these number in there. Okay, so okay, let's write down the equation. Okay, so we will have MBR divided by the area 1.9625 times 10 to the power minus 3, and its times is times 70 times 10 to the power 9. Okay, and equal to NaL is the 5.8875 yep, and aluminum is 105 giga 9. Okay, and since these two equations are equal, so we can divide it by something together. So we can divide this one. Okay, we also can divide this one. Okay, so finally we will have the where is the I don't have enough space. So okay, I just clear this. Just clear this. Okay, so finally we will have this it's 1.9625 times 70. Okay, so it's 1.9625 times 70 equal to aluminum 5.8875 times 105. Okay, so what would you get? Okay, what will you get? I think you will get this equation like this. Okay, so just write down for you. You will find it's really true. Okay, let me see. 1.9625 times 70. Divide 105 divide 5.8875. Hmm. It's a little different. Hmm. Okay. 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 Let's see. So I think you will get. I think this is. I think it's 9 MBR equal to 2 NAL. Okay. I think you will get this relation. Okay. So you got this, and then you have the initially equation NBR plus the NBR plus NL equal to 45 kilonewton. And now you from the competitivity equation, you got 9 NBR equal to 2 times the N, 2 times NAL. Okay, so you use these two together. So what will you have? So you have NBR is NAL, so it's well 1.222 NAL times 45, 36.1. 36.1. Do I missing something here? Do I missing something here? Looks like I didn't have the very correct answer. Mm-hmm. I missed something here. Sorry. AL, ABR, ABR, breast is, I miss, sorry, I miss. I missed something here. Okay, MBR its mega modulus is 105. Okay. Yeah, so that's why I didn't get the correct answer. Sorry about that. So this is 105 and this is 70. Okay, so the same thing here is 105. Okay, here is 105 and here is 70. Okay, so we will have the very different different relation. Let me check it again. 1.9625.8875 divided by 70. Yeah, I think that's the correct answer. Okay, NBR is equal to 2 L. Okay, so if you use these two equations, what will you have? Okay, if you use this one and this one, finally you will get, okay, NBR is 2. So NAL, okay, so normal force, NAL, so normal force on aluminum is equal to 15 kilonewton, and MBR, because these two add together is 45. So the MB press is 30 kilonewton. Okay, I think that's final answer, right? So okay, this is just normal force. Is it determine average in the normal stress? Okay, you need the final part. Okay, you want to calculate normal stress. So you have normal force. So you have normal force. How to get the normal stress? You just use the normal force divided by area. Okay, so let's need the final part. Okay, and the final part I think I just write here. Okay, the final part is normal stress aluminum, no stress on aluminum. Okay, it just use the normal force 50 kilonewton times 10 to the power 3. Oh, so what's the area of aluminum? Area of aluminum is this one. Okay, so it's just 5.8875 times 10 to the power minus 3. Okay, and what's the normal stress of the breast? Normal stress of breast. Okay, so those breast source is 30 times 10 to the power minus 10 to the power 3. And the breast here 1.9625 times 10 to the power minus 3. So what's that? So let's just calculate. So 15 divided by 15.887. Okay, and times 10 to the power 6 divided 10 to the power 6. So it's 2.55 megapar. 2.55 megapar. Okay, so what's the normal stress of the breast? Okay, 3 divided by 5, 1.9625. So it's 1.53. Okay, 1.53. Okay, megapascal. This is 3. Okay, did I get the answer? Well, why do I get it? Why? Why don't I get the answer? Oh, I did the reverse again? Why? Why I always get a reverse answer? Aluminum is 15. Oh, why do I get an aluminum answer? Ah, yeah, sorry. So this is reverse. Okay. So the answer is reverse. Very sorry. I did not a mistake in this video. Okay. So this is the correct MBR. NL. So NL is 15. Okay. BR is 30. Okay. L is 15. And NL to BR. To MBR. So NL is NL. Oh, MBR. MBR is 15. MBR is 15. MBR 15 and it is 30. So MBR is, yeah, well, quick get reverse. That's really look shit. Look like shit. Okay. So 30. MBR is 15. Okay, so Did I get the area correct? Yeah, area is right. Sorry about that. So the answer, this is not 2.55. So, okay. So it's 30 divided by 5.8875. Okay, so it's equal to 5.10. Okay, so this is 5.5.10 megapart. And what's the next is 15 divided by 1.9625 is 7.64. Okay. Yeah. Okay, finally I got a correct answer. Sorry, I missed something here. Okay, I also missed. Yeah, sometimes you will. Yeah, you will switch the number in your mind. Okay, so just be careful. Just be careful. Yeah, because my equation are all correct. Okay, but I misplaced the number, and then and I just if I misplace this number, even if the calculation scheme is all correct, but you still cannot get the right answer. Yeah, I'm not really very careful in this problem. So, okay, so remind you, okay, be careful when you do this engineering calculation. Engineering calculation is not that I cannot say it's difficult, but a lot of number in there, and sometimes you misplace a number, you just cannot get the right answer. Okay. So after all, so we see, okay, if you apply an external loading on the coaxial bar, you will find the inner breast will take more stress. The inner part takes a 7.64 megapascal stress, and aluminum, the shell part only take the 5.10 megapop. Okay, that is because the brass has is a harder material, stiff material, because its modulus is 105 gigapart. It's much greater than the aluminum 70 gigapart. So if you these two material form a coaxial material, the stiff material will take more stress. Stiff material will take more stress. Okay, and that means because the stiff material is the shell part. Okay, that means the shell parts take more stress. That means it can protect the inner part. Okay, the inner is. Oh, do I miss something here? Hmm. Oh, the inner part is taking more stress. Okay, so I make another mistake. Okay, the inner part is breast. Okay, so you'll see the inner part take more stress because it has stiff material. Okay, so I just saw the stiff material is on shell, but it looks like this is reverse. The core is stiff. Okay, the shell is soft. Okay, this is very strange designs. Okay, because we often think the shell should be more rigid to protect the core, but this is reverse. Ah, okay, this is reverse. Okay, maybe just okay. You say it reinforced with the core. Hmm. Okay, yeah, the core take more stress. That's true. Okay, but why? You should strength reinforcement with the core. Okay. Okay, anyway, so this is statically indeterminate problem or second problem. Okay, so I made some mistakes, so sorry about that, but I don't want to redo the whole video again. Okay, so see you in another video. Okay, bye bye. Okay, bye bye. Yeah, sorry about make some mistake. Okay, bye bye.